Welcome to College Algebra. In this lecture video, we are going to continue our section 4.3, locating the real zeros of the polynomial function. So in this video, I'm going to start out with another objective called the intermediate value theorem. What the intermediate value theorem for the polynomial function says is, if I have a function f to be a polynomial function with a real coefficient, if f of a and f of b, what that means is a and b are two different x values. I'm going to plug in my x value into my function, so the entire f of a represent a y value. So here is another x value plugged into the function, and the output is another y value. So what it's saying is, if the two y value have opposite sign, then there is at least one value of c between the two x value for which that number c is going to be the zero of the polynomial function. So if you use a graph, for example, on the x-axis, let's say here is my x value a, here's my x value b. I plug in the x value a into the function, and what happens when it's negative? Less than 0 means negative. So what happens when the y value is negative? Where the other x value b I plug into the function, and the y value is positive. So when the y value have opposite sign, that tells me that there is a number c in between my two x value, where that number c got to equal to the 0. Okay, therefore that c is the 0 of the polynomial function. So let me show you. Okay, let me show you what this theorem really means. Find the value of the following function at x equal to 6 and x equal to 7. Does the intermediate value theorem guarantee the function has a real zero between those two x values? So basically what we're going to do is graph this function and go to our table to find 6 and 7 for x value, and let's take a look at what the y value is saying. So I already entered it into my calculator. So this is a negative x to the third. It's a cubic function. So when I press graph, I see my function cross over the x-axis at one point here. So if I will go to my table, go to x equal to 6. When x equal to 6, the y value is 40. When x equal to 7, the y value is negative 4. So what that means is, when the y value has opposite sign, it guarantees that there is a 0 in between 6 and 7. Because when you go from a positive y value, which is above the x-axis, then the next x value, the y value become negative. So that means the graph cross over the x-axis, go from a positive y to a negative y. So that means it cross over the x-axis somewhere between 6 and 7. So the intermediate value theorem guarantee there is a real zero in between. Okay, so we can use intermediate value theorem give us a guide regarding to where the zero can be. We can narrow down to between these two x values. Okay, you will see what I mean in a different lecture series when we begin to actually find the zeros. Now I also want to use this opportunity to introduce you the different types of zeros. Little by little I began to mentioning these type of zeros, but I never really put a label on them. So here we go, the different types of zeros. You come find out if you actually go back to maybe like 4.1, some of these problems that we did talk about, does consist of what we so-called the non-real zeros. Okay, so this one is a real one. Because there were certain ones I purposely do. Maybe it's not in this particular section. This one right here I did. No, this one is real zeros. This is just for the multiplicity. Well, it turns out that one type of zero is called a non-real zero. Non-real zero, sometimes I will call them the imaginary zero, in the form of a plus bi and a minus bi. Alright, so you can read through all this, but what's important about the non-real zero is the non-real zeros always occur in conjugated pairs. Okay, what that means is you're always gonna end up with a positive one and the negative ones. Non-real zero means it's imaginary, therefore it will not show up on the x-axis. Just like this problem we graphed just moments ago. This is x to the third power. So what that means is I should have 3 zeros. But I only see my graph cross over the x-axis one time. So where are the other 2 zeros? The other 2 zeros will be the non-real zeros because they come in conjugate pair. They come in 2 at a time. So if the other 2 are non-real zeros plus this one, that will actually make it 3 zeros right here. Alright. Another type of zero is called the irrational zeros. Irrational zeros are real numbers, so they will show up on the x-axis. Irrational zeros also occur in conjugated pairs. Okay, they also occur in conjugated pairs. So let me kind of summarize this just real quick. And of course, the last one is called the rational zeros. So let me do it right here. Let me make this a little bit smaller. The one we will see on the calculators got to be considered as real zeros. Okay, so under the real zeros we have what is so-called the irrational zeros. Irrational zeros. And we also have something called the rational zeros. Both of these types, okay, will appear on the x-axis. We will actually see it cross or turn, okay, at the x-axis. The one we don't see is the non-real zero, just like this one. Only see it cross one time. There's one real, the other 2 got to be non-real. Okay. So the third type of zero is called a rational zero. So what a rational zero theorem says is this: let your piece of x to be the polynomial function where all the coefficients are all the coefficients are integers. Okay, gonna be integer coefficients. Now consider a rational number denoted by p over q, where p and q are relatively prime. If we pretend this rational number p over q is a zero, then p is a factor of s null, and s null is the constant term. Okay, p is going to be a factor of the constant term, and q is going to be a factor of the leading coefficient s of n. Okay, so what's going on here is this: with the rational zero theorem, the p over q, use the rational theorem to list all the potential, that's the key word right here, all the potential rational zeros we can have. Okay, remember now, rational zeros, okay, rational zeros are real, so is irrationals. Using the same example here, this zero right here, okay, this zero right here is not going to be irrational. Why? Because irrational zero come in conjugated pairs, so you will see it cross over the x-axis 2 times. So this one time it cross over the x-axis, that got to be a rational zero. And how do we find it? Well, we know based on the intermediate value theorem, is going to be between 6 and 7. But exactly what is it? We can actually use it. We can actually use the rational theorem to help us, potentially what it could be. All right. So right now everything seems a little bit vague, and that's okay, because as we move on, everything will be a little bit more clear. So here, let me help you do this P over Q thing, listing all the potential rational zeros. Potential, okay? We still got to find out which one is which. So P over Q. P is the constant term. Okay. Q is the leading coefficient. Alright, so the way we do it, okay, they're using the word, P is a factor. Okay, factors of my constant term. What are the factors of 4? 1 times 4 and 2 times 2. So these three numbers are the factor of my P. Over Q are the factors of my leading coefficient. My leading coefficient is a 1. So factors of 1 is just 1 times 1. We only got to write it down 1 time. So when we list out our potential zeros, we will say 1 over 1 is 1. You know what? Let me color code this. Let me use 1 over 1 is 1. 2 over 1 is 2. And then 4 over 1 is 4. So I got 1, 2, and 4. So these are the positive. Okay, these are the positive potential rational zeros. Remember now, factor of 4 can be positive 1 times positive 4, or it can be negative 1 times negative 4. So if I can have a positive potential rational zero, so I can have the negative ones. Okay, so I got 6 potential rational zeros. Okay, now which one is it? We're actually going to use a calculator to help us find that out. Okay, all right, let's try another one. P over Q, listing the potential rational zeros. So the P is the constant term, Q is the leading coefficient. So when we write out the P over Q, the factors of my P, 1 times 6 and 2 times 3. Over Q, factors of Q, 1 times 4 and 2 times 2. Okay, so let's try this. Okay, this can be a little bit messy. I'm not going to try to color code too much right here. Alright, start out with a 1 on top. 1 over 1 is 1. 1 over 2 is 1/2. 1 over 4 is 1/4. Alright, let's try the other one. 2 over 1 is 2. 2 over 2 is 1. I already got it. 2 over 4 is 1/2. I already got it. Okay, move on to the next one. 3 over 1 is 3. 3 over 2 is 3/2. 3 over 4 is 3 over 4. Alright, try the 6. 6 over 1 is 6. 6 over 2 is 3. I already got it. What's 6 over 4? 6 over 4 reduced by 2, that will be 3 over 2. I already got it. Okay, so these are my positive ones, so I can have what? All the negative ones. So when we do the P over Q, the rational the rational zero theorem, what it does is really help me to kind of identify, other than integer zeros, I could potentially have some kind of fraction zeros as well. So if I use this problem, for example, okay, this one right here is a little bit tricky because that's a 10. That can be 1, 2, 1, 2, 5. 1, 2, 5, 10. Okay, this is 1, 2, 5, 10 over -1. Let me go back to that page real quick, make sure I'm typing it right. Okay, if I think about it, P is this, so that's 1 times 10, 2 times 5, over Q is 1, so that is 1. So if you really look at it, since the denominator is 1, all the potential rational zeros got to be integers. But then when we graphed it, we find what? There's a potential zero here that is what? That is between 6 and 7. Okay, so I still need to know, there got to be another way to help me to find that actual zero there. Okay, because just by listing the potential rational zero, I still cannot see it. Okay, I know it's going to positive. I know it's going to be between 6 and 7 just by the intermediate value theorem. But that particular example, is actually kind of hard to narrow it down. But most of the problem is actually easier to narrow down, especially looking for the fraction ones. All right. So we will work on more of these. Okay, we'll still work on more of these as we go along in this section. Okay, then this is going to become my first step on finding. This is going to be my first step for the ultimate way to find the zeros. All right, we'll work on this some more. Thank you for watching.